Okay, let's go ahead and get started. Time to rock and roll. How's our audio? Good to go? Excellent. Some of the different address types, instead of using the old loopback address of 127.0.0.1, which we used in IPv4, we just simply have the ::1, which is giving you the ability to ping your own workstation. The link local, the FE80 address that we give you on your system is so that we can do peer-to-peer connections. So this would be one of the tools that we can use to actually give us this address so that we can do peer-to-peer. Your site local is similar to your IPv4 private addresses. This is what we would use on the inside of your network before transitioning this out to the outside with network address translation, which we'll see coming up in a few moments. Our global addresses begin with the number 2000 or 3000, depending on which continent and country you're in. Multicasting all begins with an FF address. So we talked about address resolution protocol and the fact with address resolution protocol we're resolving between your IP address and your MAC address. DNS, domain name systems. With domain name systems, what we want to do with DNS is we want to identify what your web page is. The host, the mail.corporate, which is my subdomain. Java Toucan is the domain. .com is your connection at the end. And then finally, we take a look at the way that we resolve domain name systems. DNS can be resolved back over to your full MAC address, or your IP address, I'm sorry. When we think about DHCP, Dynamic Host Configuration Protocol, this is allowing us to pass addresses out to the end user. 4 things to remember with DHCP. How many of you have kids? How many of you have ever heard of Dora the Explorer?
Heard of that.
Okay, Dora stands for discover, offer, request, acknowledge. With DHCP, your workstation is going to say, I need to find a DHCP server. It's going to send out a broadcast to discover the DHCP address. So who's got a DHCP server? So Discover goes out there to find DHCP. Your DHCP server is going to then offer you an address. Eric, would you like the address of 200, 200, 200, 200? Yes, I would. So I request that address. I would like that address. And finally, it's going to come back. It's going to say, let's acknowledge. So discover, offer, request, acknowledge, and then it's going to go ahead and say that's your address. So when we think about DHCP, DHCP needs to be pointing to your default gateway. We can also point to your DNS server. We can also point to your Win server. We can also push out a time from your NTP server out to your workstations as well. So as we start thinking about DHCP, in most cases, my router is going to push out the DHCP addresses, or it could simply be my Windows workstation or Windows server that's going to do that as well. Let's talk about address translation. So as we start thinking about address translations, there are 4 different ways we can translate our addresses. So let's talk about those 4. In most instances, we have a firewall or a router. I'm going to have an outside interface, and I'm going to have an inside interface. In most cases, we're going to use our private addresses in here. When we think about those private addresses, could be a Class A address, which would be that 10.x.x.x. Could be a Class B address, which could be that 172.16.x.x. It could be a Class C, which is my 192.168.x.x. So that could be on the inside. So generally, if we take a look at TrueNAT, nobody uses this anymore, but we have to talk about it. I've got a pool of addresses on the inside, which would be something like this, going to a pool of addresses on the outside, So as we go from inside to outside, it's a true one-to-one relationship. That means for every address on the inside, I've got a fully routable address on the outside. Those fully routable addresses could cost you as much as $1,000 a piece for the outside addresses. If you have 200 people on the inside, it could cost you $200,000. So most companies will not use NAT. Instead, they will use port address translation. With port address translation, I still have a pool of addresses on the inside, but I'm going to be going to a single address on the outside that is fully routable. So I might have the address 200.20.20, port number 1722. Anytime I am combining my IP address plus a port number, this is known as a socket, so it's uniquely identifying that combination to you. The assignment of the ports are generally going to be above 1024 because the first 1024 port numbers that we have are known as well-known ports, so we normally don't pass those out to end users. So my next person going out is going to have 200.20.20. Port number 2017. Next person going out still gets 200.200.20.20. And they might have port number 14476. Next person going out still going to get 2020, but they might have port number 57162. So the firewall or the router keep track of those addresses that we have and where we're going. When the traffic's coming back in, it looks at that address and it looks in its table and says, this is how we translate this back to your local address on the inside of your system. So that's NAT and PAT. Let's take a look at the other two choices that we have. We have something that is known as interface NAT. So at home, I've got an ISP that connects into my DSL box. It's going to do DHCP to the interface here. Because again, my workstation, or I should say the DHCP server, or DSL server is connecting back up to the ISP. My DSL is going to simply go up and say, hey, do you have an address for me? So it's sending out the discover, the offer, the request, and the acknowledgement. So the door goes on here. I'm going to probably have a couple workstations here that are connected. So down here I got a workstation, another workstation, and this workstation. And these guys are going to use DHCP to get addresses going down this way. And then they're going to go ahead and use interface NAT to connect to the interface that I have right here. It's really called interface PAT. If we looked at it, it's really port address translation because it's got an IP address and we're just assigning a specific port number to it. This allows the ISP to do a couple things. One thing is that if they want to alter their IP address that they have here, they can simply push down a new address to me and then reboot my system and we're good to go. It'll go ahead and reconfigure all of this by itself. The last one that we have, besides my interface NAT, is going to be something called static NAT. This is mainly going to be on a firewall. So this is my outside interface. This is something called a DMZ. The DMZ, there's an inside down here as well. On the DMZ, I'm going to put a web server in here. The web server is going to have an address of 172 .16.20.20. I'm going to take this address. This is not a routable address. This is one of the private addresses. So my web server's got this address, and we're going to go ahead and advertise this out on the outside as a fully routable address. I might have the address of 200.20.20, port number 80, because port 80 is going to a web server. What if it was also hosting a secure web page? What would that port number be? So again, I've got the 20.20, but port number 443. So I'm going to have two different sites in here, one that's secure and one that's not secure. So I'm translating this always to the same address up here. So this would be my static NAT. Okay? So static NAT would be the other way that we can do this. So these are really the four different modes that we've got for network address translation. So it depends on how you have your network set up and what sort of addressing schemes you want within your network. Okay, so let's take a look at what the book says. The book talks about NAT and I don't like the way that they've done this. You never do NATing with two private addresses. It's not possible, because one of these has to go out to the internet. So you can't use the 192.168 on the internet. You can't use the 10 address on the network. So basically, they're just NATing between two internal networks that they have. So we can do a one-to-one, so that's true NAT. So the NAT that we see on the board over there, that's the first one that I put in there, is a true one-to-one. The one-to-many is going to be the port address translation. So it's the many-to-one. So I have all these addresses on the inside going to a single address on the outside. So with that port address translation, again, I don't like their example because they're using private addresses on both sides. You should have a fully routable address on one of those. I would have gone to the left side external server. I put in the 100.100.100.0 because that would be a fully routable address. Okay, we got a couple questions for you. What might a router using PAT change on packets that are passing through it? So we only need to change the local addresses and ports. So the destination for incoming packets, so that'll be A, and the source address for outgoing packets. So it's going to be A and F would be your two answers that they've got. What protocol is used to find the MAC address given an IP address? That's going to be ARP, Address Resolution Protocol. For a local server, you might not need the full domain name to perform a DNS lookup. That is true. So if you're just finding it on the local network, you don't have to worry about that. You're just looking for the local name, not a fully qualified domain name, because it's not up on the internet. It's a local address. Which IPv4 address might be valid on the internet? Bravo, yep. So 127, which is A, is the loopback address. The 169 is the APIPA. The 192.168 at the bottom is private internal address. So the only possible answer would be Bravo. What network attack can only be used on local network segments? This is going to be my ARP poisoning because ARP does not cross your broadcast domains, so we don't have to worry about that one. What protocol can be used to prevent DNS poisoning? I would really hope it's DNS security. It's kind of a give me there question. Kind of like who's buried in Grant's tomb? Anybody ever watch the episode of Cheers when what's his name? The mailman was on Jeopardy. Norm, not Norm, the other guy. Cliff Clavin. He got himself on Jeopardy. He answered every single question. He had all the points in the world, and he bet everything. And the question that they asked was, who's buried in Grant's tomb? And he went, who the hell would know? I thought that was hilarious. Okay, this next module, we're going to take a look at TCP and UDP. We're going to talk about network ports, and we're going to take a look at some of the common network applications that we've got out there. So our transport protocols, we're providing our end-to-end communications. We are using either ports or sockets. Remember, a socket is an IP address plus a port number for host-level multiplexing. We have two common protocols, TCP and UDP, Transmission Control Protocol and User Datagram Protocol. TCP, connection-oriented. It's going to negotiate that dedicated two-way session. It is reliable, provides that error correction. In other words, if we don't have a packet that made it across, we can resend it. It handles that flow control. Remember, we're going to start off by sending and increasing the number of packets every time we send something out. We do sequencing to put numbers on the packets to make sure that we get them in the proper order when they arrive at their destination. So when we send out the first connection, we flip the synchronization bit. We then get back the SYNAC, so we get the acknowledgement, and then we send back the synchronization. After that, we send back the acknowledgement. So this, again, is the embryonic connection that we have. Once this is completed, then we are in a full connection. UDP, on the other hand, is connectionless. It's unreliable. It's much faster. Its uses are for time-sensitive data, so small data exchanges. When I go to a TFTP site to download my updated operating systems for a Cisco router, I will use UDP because it's much faster. It's unreliable. There's no way to tell whether or not there were issues or problems with it because there's really no error correction, or there is sequencing so we know the packets, but if we lost a packet, there's no way that we can resend that packet. So UDP is much faster, much cleaner for something that's small that I'm sending. Whereas FTP is going to be using TCP and it's guaranteed delivery. As we take a look at some of the network protocols that we have, our protocols have different port numbers. So when I take a look over on the right-hand side and I'm connecting in between my different clients and those different workstations, if I'm going to connect into the FTP server on the right-hand side, I'm going to be setting up my FTP client. So I'm going to port number 21 on FTP. They'll send back my data on port number 20. So FTP uses ports 21 and 20. If I'm going out to the web browser, it's on port 80. So I will connect into port 80 over on the outside server I'm going to. If I'm going to be connecting in with Telnet to a Telnet client, I'm coming in on port number 23. So how many of the ports should you know? You should know ports 20, 21, 22, 23, 25. Can we start again? 20 and 21 are FTP. What is 22? Secure copy, secure FTP, and SSL. Pardon? Or SSH, I'm sorry. SSL is 443. What is port number 23? It's right there, Telnet. 25, SMTP, Simple Mail Transport Protocol. You need to know port 53, DNS. Port 69, TFTP. Port 110, POP3, port 123, NTP, Network Time Protocol. Port 143, IMAP. Port 161, 162, SNMP, Simple Network Management Protocol. And port 443, HTTPS. So when you start looking at these ports, those are the basic ports. You should know those for any class, any work that you're doing in IT. Those will be the ports that you need to know. The port ranges that we have, the system ports are that first 1,024 ports. Your user ports come in at 1024 and go up to 49,151. These are assigned to applications which will register for one. Your private ports are above that at the 49,152 all the way up to 65,535. So again, we've got 3 different groups of port ranges to look at. As we look at some of the applications that we are running, we start thinking about the protocols that we are running. We don't want you running Telnet anymore. Why not? Unsecure. What's the difference between unsecure and insecure? Because if you look up here, it talks about insecure protocols right there on the 3rd line. What's the difference between an insecure protocol and an unsecured protocol? You get that look like, oh my God, I have no idea. No. If I told you that I was insecure, what would that mean? When I put on sunglasses, the mirror's on the inside so I can see the people behind me. So I'm insecure. I'm always looking over my shoulder because I think someone's going to try to get me. Do my protocols look over their shoulder all the time and go, oh my God, I'm being attacked by someone? No, it's a typo, really. It should say unsecured rather than insecure. I don't know. This has happened in almost every book that I read. My protocols are insecure. Really? They've got I'm going to send my protocols to go see a psychologist. Are no longer. I just don't get it. I'm sorry, I just like to use the English language like it's supposed to be used and not like some people use it. Anyway, when we start thinking about the secure replacements, we don't want to use something that's an unsecured protocol, so we want to combine unsecured protocols with others that will provide security. Secure socket layer, SSL, can be added on to pretty much anything that's out there. So we can also use VPN technology. We're going to see VPN coming up in the next chapter. So we're going to look pretty deeply into VPN and how it works. Another way that we can limit traffic flow and access is by segmenting my network traffic by putting in different VLANs. So this would be one of the ways that we can do this. So here are some of your remote access protocols. Telnet is not secure. It's running on port 23. The replacement is SSH, which is on port 22. We also have the remote desktop protocol, RDP, is running on TCP port 3389. There is a secure RDP, but they haven't come up with a port number with it yet. SNMP, Simple Network Management Protocol, is using ports 161, 162. It is secure only if you're going to use version 3. So it's going to use SSL on top of SNMP. We have a couple other resource sharing protocols. LDAP, the Lightweight Directory Access Protocol, has 2 different ports you need to know. The one that you really need to know is the secure port. So the unsecure is using TCP port 389. The secure protocol is TCP port 636. NetBIOS is Microsoft's ability to use multiple applications. I would never use NetBIOS if I didn't have to, so you want to turn NetBIOS off on your computer. SMB, the server message block, is used for sharing folders in the Windows environment. So SMB, the secure message block, is using TCP port 445. My FTP file transfer is using ports 21 and 20. I'm going to connect to your FTP server on port 21. You'll send me back the data on port 20. Your TFTP, Trivial File Transport Protocol, is using UDP on port number 69. And finally, NTP is Network Time Protocol. It is using UDP port 123. HTTP, used by web browsers for almost every function. It is not a secure protocol. It's using port 80. We would prefer that you use port 443 or HTTPS. It's going to use SSL, which has been replaced by TLS. So secure socket layer was considered not secure. They added in TLS or transport layer security to add in that level of security that we have. So when we take a look at TLS version 1, it's really SSL version 3.1. SSL version 3.2 is TLS version 1.2. So we started looking at the way that they put these together. That's what we have. So when I'm using SSL or TLS, it's port 443 with TCP. Some of my email protocols that we've got out there, SMTP, Simple Mail Transfer Protocol, is port 25 with TCP. The POP3 we've been talking about is TCP port 110. IMAP is TCP port 143. MAPI, or MAPI, is a proprietary exchange protocol from Microsoft used for sending and receiving emails. So your SMTP, POP, and IMAP are not secure, but you can tack on SSL on top of that and make it a secure protocol. So again, by adding in the secure socket layer, SSL is providing that tunnel between our two systems that is secure. When we think about working on a computer system, if we're sitting on a Windows system and I want to find out what your IP settings are, I will type in the command ipconfig. If I'm sitting on a Linux or Unix system, the same command with a little twist on it is if command. That's going to show me the configuration of the IP settings on that box as well. Netstat is going to display a variety of network information on my system. Dealing with my Windows system. NBTstat is displaying my diagnostic information of NetBIOS over TCP. Netstat with a -AN is going to give me what connections I have to the outside world. So it's going to show me what established connections I've got to the other world. The ARP, again, Address Resolution Protocol. If I want to be able to actually see what's on my workstation, I can type in ARP with a -A. If I want to find out what your IP address is, I can type in NSLOOKUP and then put in your web address. NSLOOKUP for www.cisco.com is going to show me what their IP address is. I can use the ping command to also find out what your address is, so it will come back and send me back the address that was responding. Traceroute is going to let me move through your network one hop at a time until I can get out to your final destination. So it'll route me through the whole network to show me how I've gotten to your system. Ping path would do the same thing. This is done within Windows. So ping path would be the command that is within Windows that will show the pathway that you're taking from your Windows machine all the way to the destination. It also comes back and tells you what the latency is. Every one of our commands says that I can go ahead and put in an option or a switch. So I might type in ipconfig /all. So that's now going to show me all the information about your connections coming off of your Microsoft system. When I take a look at the command up here, the IP address or the interface tells me one of the variables or arguments that I can use to determine I'm going out this interface or looking for this IP address. So if I'm taking a look at my ipconfig command that we see up here, you're going to see it shows my IP address, shows my subnet mask, and shows my gateway. You'll also notice that it has something in there called an isotap tunnel. The isotap tunnel is the third line from the bottom. It shows the isotap tunnel, and it's showing me a very weird address. Isotap is provided by Microsoft to begin the transition from IPv4 to IPv6. Does anybody in this room willingly want to go into IPv6? No, why not? You're just going to do the bobblehead. You do it both directions very well. What's with the no? Why don't you want to go into IPv6? Just so much more complicated? It is. It's one of those things, you know, when you jump into an airplane and the pilot turns and goes, would you take over while I go run an errand? Wait, you want me to fly this plane? Are you kidding? It's really not that hard. Unless, you know, if it's already going down and he hands this to you while he's jumping out the window, you might want to reconsider what's going on here, but, you know. So netstat with -an. Netstat's going to give me, you'll notice in here, it's showing me some of the IP addresses I've got and port numbers. So if I take a look at this bottom one that I have here, it shows me that my local address, 192.168.0.2, I'm going at port number 52575, and it's closed. If I go up 2 above that, I see that I'm going out port number 52573 to this foreign address of 104.43.164.23 with HTTP, and it's established, which means I have a connection going out to their web page. So we start looking at this, and this is going to give us this ability to look on my local workstation to find out what I'm connected to. Why would I want to do this? Is there something or some software in my system that's connecting me out to something else, and I should be aware of this? So this is where I can find out what addresses I'm connected to from my system. NSLOOKUP is the command that we would use to find out what your IP address is of your web page. They did this for 30Bird, who is the company that has written your book. They are the publishers of your book, so I can say NSLOOKUP for 30bird.com. It's going to come back and give me their address. We can use the ping command. Again, in the ping command, the things that I'm looking for here, it says reply from the 67.227.186.99. The number of bytes are 32. I cannot exceed 65,536 on the bytes because that would be the ping of death, and that's no longer allowed. Next to that is going to be my time of how long it took for that to get out and come back to me for the ping command. The last one is my TTL, or the time to live. Again, every time I go through another hop or another router, it's going to decrement that by 1. Okay? So here are some of the ports that we have. If you would please match the port numbers that we've got. So the first one is Telnet. What's the port for Telnet? 23. How about SSH? 22. How about SNMP, Simple Network Management Protocol? And wait till the end on that one because we'll have one left over. It is 161. How about SMTP? 25. FTP? FTP is 21. How about LDAP-S? 636. DNS? 53. HOP? 110, and finally IMAP, 143. Let's do this again, starting at the top. SSH, 22. Oh, I'm sorry, I should have started with Telnet. Telnet at the top, 23. SSH, 22. SNMP, Simple Network Management Protocol, 161. SMTP, 25. FTP, 21. LDAP-S, 636. DNS, 53. POP3, 110. And finally, IMAP, 143. You should definitely know these for the test. By the way, this will be a drag and drop. When you take a look at the study materials that I've given you, it is a drag and drop in there. You want to securely connect to a server via command line terminal interface. What protocol should you use? What's the only secure protocol up there? SSH. How many total packets do you need to be exchanged for a TCP handshake? See, I wish they would have just said, how many do you need for a TCP three-way handshake? That would have just been, you would look at 3 and go, no, it can't be that simple. Many times it is just that obvious. So 3 is the answer, yes. Send out a SYN, get back a SYN-ACK, replace that final line with an acknowledgement, and you are good to go. What kind of communication would be suitable for UDP? Streaming video. Anything else? Games and DNS requests. So DNS requests, online games, and streaming video. Now, see, I would also add in file transfers because I use the TFTP protocol, which is running on UDP. But that's because my experience has always been I would use the TFTP over FTP because I'm doing small file groups. And that's really what we're talking about with UDP. Your company's custom server software application needs a TCP port to listen on. What port range should it be used to configure? Or should you configure it to use? It's actually going to be the private. I'm sorry, user port is best. Private's for temporary applications, system ports for registered IANA applications, so the user port is best. So you were correct. You're welcome. What protocol would you use to connect to a shared drive on another Windows system? SMB, the server message block is for file sharing. HTTPS adds security to HTTP and uses a different port, but otherwise is fundamentally the same. That's true. So in this chapter, we took a look at a lot of information. We took a look at the network models, the data link layers, the network layers. So we looked at switches and VLANs at the data link layer. The network layer, we looked at routing and IP addresses. We looked at unconventional network devices such as voice over IP and our storage area networks. We took a look at IPv4 and v6, the different address formats, the address resolution protocols, and network address translation. We looked at the transport layer protocols, how they work, some common network protocols, how to identify common network application protocols. This next chapter that we have talks about securing the networks that we have. So in this, we're going to take a look at several ways of securing data on our networks. We're going to look at how to secure the data via transport encryption. We're going to take a look at how to harden your network. And then finally, how to monitor your network and detect threats that we might have. So as we start looking at this, we're going to begin by looking at some access control lists. We're going to look at firewalls. We're going to look at the difference between an IDS and an IPS. We're also then going to look at some other security and optimization devices out there. Now, one of the things to think about with an access control list is there's 2 parts to every access list. The first part to the access list is actually deciding which interface I want to put this on. So where's my source, where's my destination, and I got to write the lines of code that we want. So in this one, I am blocking Telnet, I'm allowing HTTP, I'm going to block FTP, and I'm going to allow SSH. So I have to start thinking about what are the things I want to allow? What is it that I want to block? Which interface do I put this on? These are the things we think of with any access control list. Now here's the problem with an access control list. Has anybody here ever been to one of those nightclubs where you go out dancing? Yep. When you go out to the nightclub, is there a big guy standing in front of the door? Grant, what's his name? Does he know this? Is that true? You're a bouncer? You've done this before. I cannot confirm nor deny. this accusation of my previous employment. Wait a minute, are you from Capitol Hill? Are you working up there? Okay. Now, when we write the access list, we have a couple ways of determining how we want to write this. It could be very simple. I could say deny, 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 and allow everything else. Or I could say permit, 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 and deny everything else. Which one's the easier way to go? No, no, no. If I did that, I would be denying all day long. I'd be sitting there writing up 20 million lines of code because I'd be denying your access to go to certain places. It's much easier to say you're allowed to go here, 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 and here, and everything else, implicit deny all. It makes my life a whole lot easier. One of my students from DISA wrote the access control list for all the routers for the military worldwide. I said, how many lines of code you got for your access list? He said 135,000. It's a lot of lines of code. Anytime, okay, so let's say that you were a bouncer in a previous life. We aren't saying you are, we're just going to say that you were at one time, maybe, possibly. So if you were in that position, what's your job at the door when someone walks up? Keep out the what? You're keeping out the riffraff. Yeah, riffraff. So would you let me in? Would you let me in? Oh! Would they give you a list of who's allowed and who's not allowed? Okay, so you got it. They come up to the door. You got the list. What do? You start at the top of the list. Does it match? No. Does it match? No. Does it match? Does it match? Does it match? And you just keep going through the list. 16 pages down. Here it is. And you go, Grant, how the hell did you get in? What the heck? But you got to let him in because he's on the list, right? So the next person comes up. What do you do with the list? Flip it over and start at the top again. Is this going to take a while if you've got 135,000 lines to go through? Are you bribing our bouncer?
It happens in the real world.
We want two. Yeah. So you start looking at it and you're asking, wow, do I have to go through this entire list for everybody that comes up, even if they got a Benjamin in their hand? I'm sorry, if you're not on the list, oh yes, your picture's on the list though. Yeah, come on in. So you always have to give half of that, I guess, to upper management. And then you go, well, he just gave me a 20, so here's your 10. So when we look at this, anytime we've got an access list, anything that approaches the interface in the form of a packet has to go through the entire list. So that list that they have over DISA of 135,000 lines is a whole lot bigger than the last time I talked to him. I said, last time I talked to you, you only had 35,000 lines. He said, we added in 50,000 sites you're allowed to go to and 50,000 sites that you're not allowed to go to, whitelisting and blacklisting. And I went, wait a minute. Don't you have an implicit denial at the end? And it looked like I just took the air out of his balloon. He's like, oh, man. 2 days later, he comes back in, and he's got a big smile on his face. I said, what's going on? He said, I got rid of the blacklisting because we don't need to block you. There's an implicit denial at the end. So all we say is go here, 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 go here. Everything else is denied. It's going to make your access list a whole lot shorter. So that implicit denial at the end becomes real important to us as we are writing our access control list. When we think about switches, port security becomes real important on the switch. So I'm going to jump back over right now. Over to my Cisco packet tracer. And I'm going to grab a switch here. Oh, we did this again. I keep forgetting that this happens. Let me grab a switch here. Now on the switch, we had talked about the fact that every single port by default on the switch is part of VLAN 1. So I can show you this right here. Here's VLAN 1, and here are all the ports. So every single port from FA01 all the way up to FA024 and my 2 gigabit ports, those are the 26 ports I've got on my switch. Every single one of these is part of VLAN 1. So how easy is it for me to create a new VLAN? So if I do a config T, I say interface range, FA0/1 through 6, switch port mode access, switch port access, VLAN 10, boom, I'm done. It created the VLANs, it went ahead and signed them. So if I say do show VLAN, there it is, just that quick. I created VLAN 10 and took those first 6 ports and put them as part of VLAN 10. So it's really easy for me to go in and segment my switch into the different VLANs that we have. Now, if I want to secure those ports, I have something called port security. So if I type in switch port, port security, and I put in a question mark, I have a couple choices here. So on each of the 6 ports that I have in this range, from 1 to 6, I can say this is how many MAC addresses that I want on these ports that I have. Let's say that I have a single port off my switch going into my conference room. The conference room is used by my upper management team, and there are 8 people in the upper management team. Does that mean I could go in and say, I want to allow 8 MAC addresses on that port? Could I then go in and identify each of the MAC addresses of each member of the board of directors and trustees and say that they're the only 8 people that get to put their ports on there? Underneath the violation, I can say, what do I want to happen to somebody who comes into that conference room and plugs their laptop in, i.e. the contractor named Eric. I walk in with my laptop, I see the port sitting there, and I go, I need to connect to the internet. I plug my laptop into their port.
And it blows up.
In what way? Too much electricity, too much power, and the whole laptop blows up. Ty, remind me never to piss you off, okay? We actually have 3 choices. My 3 choices are pretty simple. Anyone can plug their laptop into that port, but you'll not get access unless you are one of the 8. Okay? You could plug your laptop in there, you don't get access, but then we send a notification down to the network administrator that says, hey, by the way, you might want to get up to the boardroom because somebody's just plugged their laptop in. The guy's name's Eric, and here's his address, so let's do something about this. The other thing I can do is not blow them up, but shut down the port, which means nobody else can use this until they go in and fix this. So we can add port security very easily to this by simply going in and locking this system down. So it's very easy to do this. The commands are pretty straightforward. Yep.
I got every bit of that.
See how much information we've covered already?
We already went over that?
We did.
I must
You were asleep and I told him not to wake you. So I can do MAC filtering. When I set up my port security, what I'm doing is I'm saying, here's your MAC address. We only want to allow traffic from this MAC address. Now, on the switches, we have our own loop protection that's on the switch. So let's take a look at loop protection on the switch. So we got a file server over here, and I got a workstation. I just put these things together. I want to send traffic from one to the other. So my workstation is going to send traffic in. It's looking for the file server. It's going to do a broadcast out of this direction and out of this direction. When this broadcast hits the switch, where's it going? It's going to go down here, but it's also going to go up here, which means it's going to come around here, and it's going to say A is going to go, well, he's in that direction. And this is going to go, no, he's in that direction. It's just going to do this. Is that going to bring down my network? Yes. So this is what happened when they first developed switches, and they didn't think about this. So what they decided to do was come up with a solution to this problem. So they created something called STP. What is STP? It's what? It's a little can of oil about this big. Now, I will tell you right now that Cisco switches do not come with STP in them. You get that funnel that you use to put your ones and zeros in there, and you take that can of oil and you pour it in. It's going to take you a while because it's pretty thick. I am amazed at how thick STP is. But it made your car run pretty good if your car was smoking. STP stands for Span and Tree Protocol. So I'm doing a class for this entity called SAIC. Who's SAIC? They are contractors that work with the Department of Defense. So I'm working with them. They're in my class down in New Orleans. We're going around with introductions. So we get to this young kid. This young kid looks up and he says, "Hi, my name's Billy. What everybody calls me, STP." And I walked over to the board and I drew that STP sticker and I said, "Your daddy named you after a can of oil?" And he's like, "No, sir." He says, "Dave in the back, I'm my boss. He called me STP after Span and Tree Protocol." And I went, "How long you been working with Dave?" He goes, 2 weeks. And I said, 2 weeks is all it took? He goes, "Oh, no, it only took 3 days for him to call me STP." I went, "Billy, what'd you do?" He said, "Oh, well, it was my 3rd day of work. We were up there in Little Rock, Arkansas." He said, "I was going through the server room and I had 3 switches in my hands. I couldn't see where I was going. I tripped over a cable." He said, "I reached down, I picked up that darn cable and I ended up plugging it in the wrong port." He said, "Within about 35 seconds, there's people running all over that server room trying to figure out what I just done did." I'm going to remember that line for the rest of my life. What I done did. I said, "What did you done do?" He said, "I plugged it in the wrong port." The company had turned off Spanning Tree, and he said, "I ended up bringing down the entire network just that quick." I said, "How big was the network?" He said, "Well, this is for a company called Entergy." Have you heard of Entergy? They run the power grid all the way from North Florida, all of Georgia, all of Alabama, all of Mississippi, all Louisiana, half of Texas, and all of Arkansas. And he said, within 35 seconds, I brought down the entire southern power grid. He said it took him 2.5 hours to figure out what I'd done and get them to fix that. They had turned off Spanning Tree. Spanning Tree, a little bit different here. Spanning Tree does this. Spanning Tree says, look, you got these 2 switches interconnected. So what it's going to do is it's sending something called a bridge. There's a G in there. Bridge protocol data unit. Every 2 seconds down the pipes to the same location. So switch B is receiving BPDUs from the same switch on 2 different interfaces. Switch A is receiving BPDUs on 2 different interfaces on its switch. This is indication that there's a loop, which means Spanning Tree is going to kick in. When Spanning Tree kicks in, the way Spanning Tree is going to do this, it's simply going to come in and say, we're going to forward, and block. I don't even have to think about this. It's going to do this by itself. It immediately goes ahead and does something like this to block what's going on. So let me just show you real quick if this is going to let me do this. See real quick if it does or not. Nope, it didn't. I have to do this. Nope, I'm not going to go there and show it to you. Actually, I'm going to have to now. Clicked on the wrong thing. I just tripped over my own cable. Damn it. Okay, so I got a switch here already. You grab another switch. And let me interconnect these guys. So if I'm doing a like system to a like system, I'm going to be using a crossover cable. So my question to you is this: did I just create a loop? Yes. Now spanning tree is going through a process right now. It's having an election. What it's doing is it's looking at the priority number that we have on each one of these switches. The priority is 32,768. To it, it's adding your MAC address. Whoever has the lower MAC address becomes the root switch. So one of these two is going to end up with 2 green lights on it, which means that's going to be my root switch. So the one on the right becomes the root switch. It has 2 ports in forwarding, just like my diagram does over there. So it's got two ports in forwarding. The green light's a forwarding. The lower light that we have over here on switch 0 is a blocking port. So I did not ask spanning tree to kick in. Spanning tree just did this. So by default, spanning tree protocol is built into our systems. It's going to automatically do this for us. We don't even have to think about it. So it's going to say, here's my primary or my root switch. Here's my secondary or my secondary root switch. So it's very simple for it to go in, jump in, and actually do that for me. I apologize because it just killed our slides. So I'm going to have to come back in and do this again. Let's bring it halfway down. So that loop protection is built in, so immediately it takes care of that. Flood guard would be one of the other switch security features that we have, so this is going to protect against additional network attacks where someone's going to be just launching all these flooded attacks against my system to try to bring everybody down, overwhelm you. As we start thinking about firewalls, firewalls are interesting because of the paradigm that is built within the firewall itself. So let me jump back over to my other screen here, and let's take a look at firewalls. When you go out and buy yourself a firewall, there are 2 basic interfaces. There is an outside interface and an inside interface. And these are default because generally you're going to buy a firewall that's got 2 interfaces. If we're going to add a 3rd interface, that DMZ, we're going to pay more money for it. This is known as a dual-homed firewall because it's got the 2 interfaces. So by default, it gives me some security levels in here. This has a security level of 0. The inside has a security level of 100 by default. And if I were to add in a DMZ out here, my security level here is somewhere between 0 and 100. I'm going to give it a security level of 50. Now, one of the things to look at with this is that there are some rules in place. It's called the adaptive security algorithm. And it says that I can send traffic from an interface with a higher security level to an interface with a lower security level. Where can I go from the inside? I can go anywhere. So from the inside, I can go to the DMZ, or I can go to the outside. Where can I go from the DMZ? Only to the outside. Where can I go from the outside? Nowhere. Do you like these rules? Basically, it says, look, I want to send some traffic outside. I'm allowed to do that. Is that traffic allowed to come back in? Well, actually it is. As we begin sending our traffic to the outside, we are building something called a stateful table. Stateful because I'm using TCP. So if I'm sending traffic to the outside, this is keeping track of my addresses on the inside, traffic, my address on the outside, and the type of traffic going out. If I'm sending a TCP packet out, what sort of flag am I flipping to go out? The synchronization bit. The SYN flag is set going out, which means it's keeping track of all this in the stateful table, which means what kind of flags are coming back? The SYN ACK is coming back. So we're going to go ahead and allow that. So by building this table, it keeps track of where I'm going and what I'm doing. Now, I don't know if I should tell you this story or not. This is one of the most embarrassing moments of my life. What I done did. Oh. I left Silicon Valley College. I went to work for a company called SiteRock. One of the things that we did at SiteRock was that we host people's websites. We were hosting eBay's website. They were paying us $10,000 a month to host their webpage and watch it. We would call them up if their webpage went down. So we were courting IBM. If we brought IBM on board, they were going to bring us 85 new clients at $10,000 a month. How much money is that on a monthly basis? $850,000. Is it worth courting them for this? Absolutely. So my boss comes to me, he says, we're going to build a honeypot. What's a honeypot? It's a device there to lure people in. So we're going to lure IBM in. So I'm over at my cubicle building the honeypot. My boss, Anil, comes over and he says, so, how's the honeypot coming? Yeah, it's almost done. It's 5 o'clock. He said, let's go to lunch or go to dinner. I went, well, first off, I don't have any money, but secondly, I was going to head on home. And he goes, I'm paying. Okay, I'm going. So we go out to a really nice Chinese restaurant for dinner. Before I leave my office, my cubicle, I log off my system. I don't shut it down. I just simply log off. Anil and I go to dinner. We come back, and you can hear my hard drive just going. And he goes, I thought you logged off of your system before we left. I said, I did. He said, why is your hard drive running right now? I said, I have no idea. He goes, have you loaded any new applications on this as of late? And I went, well, you know, I can't think. Oh. I got some new Allman Brothers songs and some new Eric Clapton songs. I'd never heard any of these before. What did I connect it into? A program called Napster.
Oh my God.
And he goes, you do know that Napster's not secure. And I went, no, you don't understand. Napster's secure because we're behind a firewall. And he goes, do you know how firewall works? And I went, apparently not, because I think you're about to tell me. And what he said was, if you initiate traffic from the inside, i.e., I open up the Napster connection to go out, it builds into my table to allow Napster to come back in. You see where the problem is? See how quickly I got educated? So Anil said, I need you to go through everybody's machine in the office and make sure they don't have Napster. Yeah, I got nailed on that one. Even though you have a firewall, if you initiate traffic on the inside to go out, that traffic is going to be allowed to come back in, which means that unless you have some way of protecting yourself from something like Napster, they're going to send that traffic back in. So this is how your basic firewall is set up. This is now a 3-homed firewall because there are 3 interfaces on this. So when we take a look at the firewall itself, this is my network firewall, the outside, the inside, and then over there I've got a host firewall. This is going to be the firewall that's sitting on my workstation. So as we start taking a look at some of the filtering types that we have, it could be stateful. That table I put over there is a stateful table, which means it's looking for TCP traffic. UDP traffic is considered stateless because it doesn't build this 3-way handshake that goes on. Now we also have something called the application layer firewall. When we look at the application layer firewall, what's happening with this guy is I want to do some deep packet inspection. Here we are sitting on a military base right now, and I got people sitting overseas on a military base. Is there any specific traffic on this military base that you do not want leaving this base? What might be stamped across some of those documents that you don't want leaving this base? FO, what would you call me? What'd you say to me? Might it have the word secret on there? Or top secret? Or for your eyes only? One of those little stamps. So if I have a firewall, I can do what is called deep packet inspection at the application layer. I'm looking for the word secret, but I don't know if secret's in uppercase or lowercase. So I'm going to go ahead and spell out the whole word secret. I'm going to run out of room. So uppercase and lower R there. So I'm going to spell it out, secret. When traffic is leaving here and going out, it's going to say, does the S match? Yes. Does the E, does the C, does the R, does the E, does the T? Yes, it does. So you could get flagged for sending out your grandmother's secret chocolate chip recipe at Christmas time to somebody else because it gets flagged as seeing the word secret going out across. Somebody might see that and send it to your boss and go, hey, we flagged this. We got to take a look at this. And you look at the file and go, oh, that's cool. Can I have a copy of that recipe? So we can go in and do deep packet inspection. So at the application layer, we can start looking at the traffic flowing through our systems. So you could look for something like for your eyes only would be another thing that we could look for. So these are the things that we're looking at in our network as we watch the filtering types going through. The devices that we have sitting up on my DMZ or my untrusted LAN are called bastion hosts. That's going to be my web server, my DNS server, and my email server. So these are devices that are sitting on my DMZ, and I'm putting them up there because I want to be able to capture traffic from the internet coming down to those, but I don't want them on the inside of my network. Should they get compromised, they will not affect the inside of my network. So that DMZ and the ability of being able to put rules in there of how traffic flows between these is going to help protect us. So if I've got a dual-home firewall, it means it's got 2 interfaces. If it is a 3-homed firewall, it means it's got 3 interfaces. One of the things to think about with network access control would be things like my guest network. If I have guests coming into my office, do I want to grant them wireless access to get out to the internet? Maybe not in your office, but my office I will. So if I'm a doctor and I got patients coming in, I want to give them access to the internet. We think about that guest network. Could I put in a second DMZ and say, here's the access point. You can go from here to the internet, and that's it. That's the only place you can see. I can be very specific about that. So we think about that posture assignment or assessment that we have. If we have certain clients or if we have maybe some partner nets that we're working with, we can quarantine the network and we can limit who has access to what. So we can be very specific about the security rules that we put into place. Now we can also put agents on our systems. and on our workstations and our routers and switches, which can either be persistent or non-persistent, in that if it's persistent, it's resident there, or if it's an agent, we can put it in as non-persistent, which just says it's there for this moment until the system reboots. We're using that to limit who has access to our system and what they can see. With my firewall rules, when you get a chance to take a look at those files that I've put up on your laptop or our laptops that you're borrowing, one of them is going to be a firewall, and it's going to say put in some firewall rules. They're going to say, here's my source, here's my destination, here's the protocol, here's the port number, and are we allowing or denying this? Take a look at that. That's one of the things that you'll have to do on the test. It's pretty simple. It's pretty straightforward. They're all pull-down menus, so when it says, what's my source address? You read the first line of it and you go, here's my source address. You come down, find the address, click on it. That's my source. Here's my destination address. Here's my port. Here's my protocol. So pretty straightforward in doing something like that. Let's take a look at our intrusion detection systems. I've had the opportunity to teach the IDS's IPS classes for quite a few years. So if we take a look at the internet here, your ISP, sending traffic down to a hub and then down to either my firewall or my router. We're going to come out of here down to my IDS. This is known as the monitor side. And the side is known as command and control. So this is my command and control. So this is a switch. And this is my inside network. Now, the problem with this is that when traffic is coming in, no, we want red first. When traffic is coming in and it's attack traffic, it's coming in this way. And it's also hitting the hub and coming down to my IDS. What can my IDS do if it figures out that we're being attacked? It can block it from here, but what can it do here? What's with the nothing? Can't do anything. Unless my IDS and my firewall and router, if these guys come from the same manufacturer, we can marry these together. By marrying them together and coming in through command and control, could my IDS see that Grant is attacking me from the 200, 200, 200, 200, and rewrite my access control list right up here and say block 200, 200, 200, 200. Could we do that? Absolutely. Grant, what are you going to do if I blocked you from attacking my network? Oh, man. Can't you just leave? You're just going to keep doing this, aren't you? So now you change it to 200, 200, 200, 100. I'm going to come back in here and write a new access list here to block your 200, 200, 200, 100. Now what are you going to do? Oh, man. Now you're at the 200, 200, 200.50. But wait a minute now. This is the third time you've come from the 200 network. I'm just going to block all 200, 200, 200, 200. Dot zero. Now what are you going to do? Oh, man. We could keep this up all day. I'm just going to keep inserting line number one. Okay? So Cisco looked at this phenomena and said there's a better way to do this. Could we possibly go from my ISP and put in an IPS before coming down to my firewall or router? Would that be a better way of doing this? So you attack me from the 200, 200, 200, 200, blocked. 200, 200, 200, 100, blocked. 200, 200, 250, blocked. Just that quick. Boom, 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 boom. Keep it up. Keep sending in your traffic. We're just going to keep blocking you. Makes my life pretty easy. Now here's the problem that we run into with an IPS right up here. What sort of throughput do you want for this device right here? The very first one Cisco came out with ran at 135 megabits per second. Is that good enough for you? No, what do you want? You want what? You want 10 gigs. I want your wallet. Let me have that wallet, man. I want to see that American Express. Because you know how much that box is going to cost? Your 10 gig IDS fits inside of an ASA 5585. So your IDS IPS fits right here. It's a little module that sits inside of this box that we got right here. So it's a pretty big module that fits in here. You know how much the 5585 is that handles this thing? $750,000. That's not even including this guy. How much for your IDS IPS that runs at 10 gig? $250,000. How much you pay for this combination? $1 million. You're not going to just need one, you're going to need three. So I'm going to need that $3 million before the end of today. Matthew's going to collect that before we leave today. So here's the thing. Where's the best placement for your IDSs versus IPSs? Your IPS is best placed right up here between the ISP and your router. Your IDS should be sitting up here. So my IDS box is going to be sitting off an interface here. So that's a D, not a P. So that's an IDS. So if these guys right here are launching attacks against each other, copies of their traffic will flow up here. And we will let the IDS know that they're attacking each other, but there's nothing we can do about it. Your intrusion detection, remember, is passive, whereas my intrusion prevention is active. So when we take a look at these are the ways that we set this up. So if I want to be setting up an IDS or an IPS. Now, we talked about the firewall earlier and the fact that I've got a DMZ. In the DMZ, I'm going to have a web server, an email server, and a DNS server. Those boxes should be handled by a host IDS. What's a host IDS going to do for me? Host IDS is going to lock that box down so that nobody can make any interactions with the box except for what is allowed. So if I want to make changes to the box, I'm going to have to go back in and remove the host IDS, make my changes to the box, and then put the host IDS back on here. So when we start taking a look at the way that we set this up, with my IDSs and IPSs, we have a couple choices in the way that we put these together. The first one is signature-based. So you are only as good as your latest signatures. If you got your signatures 2 years ago, you can kiss off your network because it's going to be down pretty quickly. So you want your signatures being updated on a daily basis, hopefully every hour, every 10 minutes or so. You want the new signatures. We can set up the IDS IPS to also look at behavior. So we can look at certain types of protocols, knowing that certain times of day we've got certain protocols. We also know certain patterns of behavior. We know that certain times of day you have more people on your network and certain times of traffic that are coming through. As we take a look at the results of the IDS versus IPSs, we are always looking at the results as either being a true positive, the attack has occurred, the IDS recognized it. True negative, the event was benign, there was no trigger or alert that came out. The false positive, the event was benign, but the IDS mistook it for the attack. False negative, the attack occurred and the IDS mistook it for a benign behavior, and we allowed that traffic to come in, and it's going to bring down our network. So it's the same thing that we saw before when someone was coming into our office as far as the true positive, true negative, false positive, and false negative. So when I take a look at my IDSs and IPSs, what we have going on here is the WAN's coming in through my firewall. It's going to hit the network intrusion or in network intrusion prevention. So all the traffic's going through that first. Off of my switch, I've got my network IDS, which is there to see if people are attacking each other off the switch. Up here, I've got my HIDs. So my host IDS is going to lock down that one system. And back up here on my servers, I've got my HIPs, which is my host IPS, which is watching for my traffic that's flowing through that in case anybody were to try to attack that. When we take a look at honeypots, honeypots are decoy systems. Is it legal to put a honeypot out there? I can lure you in with a honeypot or a network of honeypots, which are called honey nets. So what we're doing is we actually put in a weakness or a flaw in the system because we want to see you coming into this, bless you. So the honeypot is there to lure you in. It is legal to do that. Many times we're doing this for testing. Many times we're doing it because we want to lure somebody in. I want to do it because I want to see the new tools that you're using to hack my network, because then I want to find out how I can get my hands on those tools. So it is legal to have you coming into a honeypot, but if I redirect you back over to a pedophile site, that would be considered not entrapment. That is entrapment, that's not enticement. I can entice you in, but I cannot entrap you and send you to a pedophile site or something like that. What's that? We talked about the application layer security and being able to do some deep packet inspection up on the firewall. We also have this ability if by chance you're running a web application server. We have something called the WAF, which is the Web Application Firewall. This is firewall software that sits on your web server. So this allows us to go in and actually protect that web server. We can also use content filters. Content filters are wonderful devices, most times, for blocking your traffic, as long as they're turned on. There are times when we get software that we can use to blast against your content filter, such as a WebSense server. We can bring that down pretty easily. So yeah, when you start looking at some of the web filter software that's out there, I love the fact that with your porn sites, I know that at one time they wanted to go in and make all the porn sites have an extension of not .com, but a .xxx. That way we knew they were porn sites. We could block them very easily. But if you go to something like WebSense, WebSense says, oh, all porn sites are listed here, and you just put a big red X. I don't want anybody going to the porn site. So you can block it very simply. Now, in the ethical hacking class, we gave you a tool to bring down WebSense for 15 minutes. So basically, you launch the tool, you blow up WebSense. For 15 minutes, you can go anywhere that you want on the internet, and then WebSense will come back up. So it's real interesting when you start looking at some of the ways that we can set up these content filters that we've got. We want to think about doing load balancing. Anytime that we've got traffic flowing through our system, we want to be able to have multiple systems capturing this traffic. We can do multiple systems with routers. I can run load balancing between routers. I can do it between firewalls. I can do it between my Windows servers. So I can go ahead and set up my servers to actually be able to do this. So if one server is getting overwhelmed, the other one can take over for it. So this is a great way of being able to load balance some of my traffic. So things such as my SSL, my data compression, health checking, offloading some of my TCP and some of the buffering for it. Priority queuing, which is what we're using for voice over IP with quality of service. I can also do content caching. So anytime you're going out to a website more than once, we cache that information. We can get out there very quickly. Now we have something that's called a proxy server. A proxy server is going to go out to the internet on your behalf. In most cases, when we do this, you are on the inside of the network going out to the outside. We have a proxy server that's going to go out on your behalf. So it's going to take your inside addresses that are not routable, change them over to a fully routable address, and go out to your web page on your behalf. It's going to keep track of where you went and what you did, so next time you go out there, it happens much quicker. In most cases, we are doing a proxy to go from inside to outside. Only once in my life have I ever set up a reverse proxy to go from outside to inside. We had to push some IP addresses and NAT down into some phones and workstations that were inside of a bank branch that we had. So I did not know that was even possible at the time, but we did a reverse NAT to take it from outside to inside. Most times when we're looking at proxy, we go from inside to outside. So reverse proxy just takes it the other way. One of the best tools out there nowadays, I always love the fact that they are giving us these new acronyms. UTM is Unified Threat Manager. The UTM, one of the reasons Cisco moved to the ASA, so up here on the whiteboard is still that ASA 5585 that runs at $750,000. Cisco moved away from the PIX firewall and into the ASA. Why did they do this? They called it the Adaptive Security Appliance. Think about those appliances at your house. What the heck is an appliance? My refrigerator, my washing machine, my dishwasher, my stove, my oven. Those are appliances. They called this an appliance, and I went, what's it going to do, cook my cookies for me? So when they call it an appliance, they're adding additional capabilities. Your firewall nowadays has a small set of signatures to do IDS and IPS. It has the ability to do content filtering. It has some anti-malware built into it. It's got a DMZ interface. It does natting. It does proxy servers for me. It acts as a VPN endpoint. It will do network access control for me, provides posture assessment for me, and it does industry-based regulatory compliance checking, and it will actually print out reports for certain industries. Would this be the box you want to buy instead of a firewall? You want the Adaptive Security Appliance that gives you UTM capabilities? Are you going to pay more for this? Yes. Cisco's not the only company that does this. There's another company out there called Juniper. Juniper also makes a unified threat manager. It's known as their SX series, SX210. Is a firewall, switch, router all built together with a lot of the same stuff in here. The one thing they forgot to put in here was it has routing protocols in there. So it's giving me even more capabilities. So UTM is really where we're starting to move in our industry. Let's take a look at some of the questions that we have. So the first one, your access control list is based on which assumption? Implicit deny, yes. Unless it's explicitly allowed, it's implicitly denied. When configuring an IDS, you might want to allow a few false positives to make sure you never get any false negatives, but not the opposite. That is true. False negatives are okay, but false positives, somebody who should never be in your network has gotten in, so that is not what you want. You're configuring a router, you want to check the properties of incoming traffic before passing it on. What will this require? Configuring an access control list, yes. What kind of proxy would you use to mediate communications between the internet-based client and a LAN-based server? If you take a look at the order in which they put this in, I'm going from the internet to a LAN-based server from outside to inside. That's a reverse proxy. What sort of topology is displayed here? How many interfaces on the firewall? 3. So it's a 3-homed firewall. NIST defines the standards for unified threat management devices. Actually, it's not even a defined standard at all. It's a marketing term. You ever heard of the marketing term ethical hacking? Yes. Would you rather take an ethical hacking class or a vulnerability analysis class? It's the same class. But why do they call it ethical hacking? It's marketing. It sounds romantic. I'm an ethical hacker. This is ethical hacking. You're putting a good guy and a bad guy together. I'm an ethical hacker.
No, good guy making bad decisions, but
Good guy making bad decisions. That's called a CEO. Which of the following is an example of a load balancer scheduling method? Round robin, yes. So that would be how we move the traffic around. Okay, I got 17 minutes to finish out this one module. So we're going to talk about the transport encryption. Remember, as we send traffic from one location to another, we want to make sure that we are encrypting that information from one location to another. So we're going to take a look at how cryptography fits into the OSI model. We're going to talk about SSL and TLS. We're going to talk about the secure application protocols. We're going to talk about Wi-Fi encryption. Finally, we're going to finish out today, or maybe start tomorrow, with VPN technologies. So let's take a look at the OSI model. OSI model predates any modern cryptography. When we take a look at IPsec was added on after the OSI model came out. So they came back and they went, oh, wait a minute, let's go ahead and put this in at the networking layer. So we think about the way that the cryptography fits in this. You can do upper layer encryption. You can do an SSL type of thing. You can do lower layer encryption. I can come back in and encrypt the data that's there. So there are potential problems with the network headers and traffic shapers, because if I've encrypted all the traffic, you don't know where it's coming from, where it's going to. We're going to take a look at how to solve those problems and how to look at that. So in the upper layer protocols, we're looking at SSL. So SSL went from version 1.0 to 3.0. The 3.0 is equivalent to transport layer security version 1.0. So then it came out with TLS version 1.1, also known as SSL version 3.1. When they came out with TLS version 1.2, it's called SSL version 3.2. Somebody never wanted to get rid of the SSL or the secure socket layer name, so they just keep SSL/TLS together, and the newer numbers are actually identifying transport layer security. So SSL was found to be vulnerable, so they came up with transport layer security. We can do certificate-based encryption as well, so asymmetric key exchange. So I can encrypt things at the application layer with my certificate, so I can go ahead and encrypt your data with either your public key, and you can decrypt it with your private key, or I can encrypt it with my private key, and you can decrypt it with my public key, which means it came from me, so we can take a look at certificates and do it this way. So we can also do the symmetric bulk encryption. So all of this is done with SSL and TLS at that upper layer. We have these cipher suites that we use combining together, so I can do SSL along with VPN. That is called a cipher suite. So we'll see those coming up a little bit later on. So some of my SSL applications, we're going to do HTTP over SSL. So it's HTTPS. We can add SSL over to FTP with FTPS. We can add it into our emails. Our SNMP version 3 is also running SSL. My EAP, my extensible authentication protocol, I'm going out to a third-party box for authentication. That's going to use transport layer security. We also use the SSL VPN, so this would be another SSL technology that we can use. Now, my SSL appliances will have what's known as the SSL decryptor inside of it, which allows then someone to look inside to decrypt the package to see what's going across my wire. I might use this to see if the word secret or for your eyes only is on my data going across. So that's what the SSL decryptor would do for us. Now we talked about the fact that Telnet is unsecure. It's in clear text. So are a lot of my remote login technologies, such as protocols that are being used by Linux and Unix. So RDP would be another one that is unsecure. So we want to make sure that we can secure these. So again, if I'm going to replace Telnet, I want to use secure copy. I want to use SSH. So all of these commands are running on port number 22. So this would be a way of securing any file transfers that I'm doing. So these do use public key encryption, so they're using the X.509 public key cryptography standard that we've got, which is worldwide. I can secure my emails. So we want to secure not just the message text, but any transfer of data as well. So secure MIME. MIME is the multi-purpose internet mail extension. So they added in secure MIME, which is added in that X.509 certificate. So most of your modern email protocols will use this. So Gmail uses it, Earthlink uses it, Hotmail uses it, PGP uses what is known as the Open PGP certificate on the Web of Trust model. There's both the commercial and the free version available to you, so both of these are good choices to use. When I take a look at voice over IP, we always think about the fact that my protocols are not secure for voice over IP. However, if I'm using the real-time transport protocol, I can add in TLS to that and get secure RTP. So this is SRTP, which means that I can encrypt the voicemail going from one location, or your voice going from one location to another, which means if somebody captures it, they cannot listen to your voice unless they have the protocol and the key to decrypt that. Wireless is important to us. Wireless also has the ways, we've talked about the three different technologies there, the WEP, the WPA, and the WPA2. So the WPA, the WEP, of course, is the wired equivalency privacy. So WEP is not secure because of the RC4 initialization vector. Ron Rivest came up with it in 1997. It was broken 2 days after it was accepted by the IEEE. WPA, the Wi-Fi protected access, they increased the initialization vector from 24 bits to 48 bits, but they use the same encryption algorithm of RC4, so it's still flawed, which means someone can get in there. But you can use AES with the CCMP, which is the cipher chaining that we looked at a little earlier, so it's adding in another level of security there. The best thing you can do for wireless is to use the WPA2. You're using AES is the strongest Wi-Fi encryption, and again, this is much better than any of the other protocols that are out there. So we've got a couple of authentications. Now, on the test, you're going to get a Wi-Fi hands-on exercise. You'll see it in one of the files that's now up on your laptop. Go through that. I can't give you the actual question, but it's going to show you the things that you need to know. They're going to ask you which one of these is the most secure, WPA Personal or WPA Enterprise. The Enterprise is much more secure. So you're going to take the Enterprise, I'm going to go back a slide, combine that with the AES, bring those two together, and you've got yourself a very secure protocol. So that's what you want to do. You want to use WPA2 with AES and WPA Enterprise, and that's going to give you the best security possible for your wireless. So the rest of it, it's just finding the addresses and copying and pasting addresses into that, and you should be good to go. I think I've already given you 4 of the 5 questions you're going to get on your hands-on. I'm not going to tell you which one is the 5th. And make that one be a surprise. But if you search for it, you'll find... What's that? Okay, so VPNs. Do I have time to do VPNs? I got time to finish out this chapter and do a VPN. So let's take a look now at the VPN. This is my file server here at the office. So this is the corporate office. So this is going to be my branch office. I'm just going to make that a firewall. A switch with a whole bunch of people on this. And back up here, we're going to go ahead and, no, we don't want that from there. Sorry. This is my house. So we got a couple of different places here that we want to be able to connect into. So within a VPN tunnel, we have a couple things to look at. With VPN, I have two modes I'm going to take a look at. I'm going to take a look at the transport mode, and I'm going to look at the tunnel mode. When we think about the transport mode, can anybody tell me what the HIPAA regulations are for your personal medical files? If I'm in the hospital and I'm sitting on a workstation because I work in the hospital and I'm going to send your medical files to the server, are there any requirements on how I set this up and send it? Must it be encrypted? Yes, it must be encrypted. Why? Somebody captures your personal information, the hospital could be sued. So if this is inside the hospital right here, so this, my corporate office is over there, this is my branch office, I'm in the little hospital here, and so I've got a data that's going between workstations, or I might even have a small file server over here that's going to house your data. So within this environment right here, we're looking at this as being the transport mode. So in the transport mode, again, if we think about our data, I've got my data, either a TCP or a UDP header. Outside of this, I got my source IP, my destination IP, and I got my source MAC and my destination MAC. So if I'm sending data from here to here, I'm going to encrypt only the data. Why? Because if I think about my source and destination IP address, are these both in the same subnet? Same network? Absolutely. So I don't need to encrypt this. My source and destination MACs will also be same workstations. So all I have to think about in transport mode, because this is inside of my office, is to only encrypt the data. Does that make sense to everybody? Now let's go ahead and take the data between my remote office and my main office. I'm going to take the data from this workstation right here. I want to encrypt that data and send it over there. So as I start thinking about this, I'm going to encrypt the data from this spot to this spot. Why am I encrypting it just from here to here? Why am I not encrypting it here? Remember the deep packet inspection? I'm looking for certain words so people can't steal stuff from me. So I want to begin the encryption on the outside of the firewall to the outside of the firewall. So this is my tunnel mode right now. So when we take a look at the tunnel mode, what I have here is my data, which is being encapsulated by either a TCP or a UDP tunnel or header. Outside of this is going to be my source IP and my destination IP. Outside of this is going to be my source MAC and my destination MAC. So when we take a look at this, I'm looking at this guy as being my source address. So this is my source IP. What's my destination IP? Main office file server, right? So this is the destination IP. And if I start looking at my MAC addresses, I think this is going to be my local network first. This will be my second local network. This is my third local network. And this is my fourth local network. The problem with this is that, am I encrypting it from here to there? I am not. I'm encrypting it from here to here. So when I'm defining my source and destination IP addresses, I have to define where I'm beginning and ending my encryption. But I still have to know that I'm sending it from this workstation to that server. So what we're going to do in tunnel mode is we're going to encrypt from here to here. So this is where we are encrypting right here. And that's for tunnel mode. Okay? Now the problem that we have is this is the data that's getting through, but I'm not encrypting from this spot to this spot. I should not have put encrypting in there. Let's take that out. My fault. This is my data. This is my source. This is my destination. I'm encrypting from here to here. What I'm going to do is I'm going to add a new source IP and a new destination IP. This is where I'm encrypting from. So when I do this, I'm saying, here's my new source. So my new source will be this side. My new destination is going to be that side. So I'm putting a new header on this because this has all actually been encrypted. That is right, I am encrypting this before I send it across the wire. But this is where I'm beginning and ending the encryption out here. So this stuff we can't see. So we have tools that will actually go ahead and encrypt this, but I've got to put a new IP. If I'm going to add a new IP to this, is it going to make the file bigger? By about 200 bytes. So what must I do to my data before I add another 200 bytes to this whole thing? Shrink my data down by 200 bytes. If you were to go into the firewall right now and say, I want to put in a tunnel mode, the first thing it's going to tell me is we're no longer going to be setting up our normal packet size of 1,500 bytes. It's now 1,300. It's got a little button that tells you that this is already going to happen. It's not asking you if you want to do it. It's telling you it's going to do this. Why? Because it needs a new set of headers on the outside of this. So we'll continue this discussion tomorrow when we come in. So we'll see you guys tomorrow at, what was it, 05:30? Pacific time. Or do you want to shoot for 03:30 Hawaiian time?